Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of our show. Today, bring you another awesome guest involved in creating a better tomorrow for so many people out there. Today, we have the honor of being joined by Dr. Aubrey DeGray, President and Chief Science Officer of the Longevity Escape Velocity Foundation, or LEV Foundation, an organization focused on proactively identifying and addressing some of the most challenging obstacles on this path to the widespread availability of effective treatments to prevent and reverse human age-related diseases. Dr. DeGray is internationally recognized as a visionary biomedical gerontologist. He was the one that devised the strategies for engineered negligible senescence, this comprehensive set of methods to ultimately rejuvenate the human body and prevent the age-related ill health and mortality that comes along with it. And along the way has co-founded multiple nonprofit organizations, including the Methuselah Foundation, the SENS Research Foundation, and now LEV Foundation, where he's specifically focusing on enabling and accelerating the clinical development and translation of some of these interventions. Dr. DeGray got his bachelor's in computer science, his PhD in biology, both from University of Cambridge. He's the author of the Mitochondrial free radical theory of aging, ending aging, and a couple hundred academic papers. And he is also a fellow of both the Gerontological Society of America and the American Aging Association, sits on numerous advisory boards of scientific journals and research organizations, and needless to say, a very prolific speaker that represents this area throughout various conferences and events worldwide. Honored to have him with us today. Dr. Aubrey DeGray, thank you so much for taking the time to come back on the show.
Well, it's my pleasure. Thanks for having me back.
You know, Aubrey, it's really been interesting. Why I've watched you for the last 20 years or so now, and sort of seeing the evolution of your work, everything, from the Methuselah Foundation to SENS and now into LEV. And while sort of this overarching concept that you created in terms of sort of the divide and conquer approach to these various components of what make up aging, it's only now with LEV that you've really sort of stepped back and added to divide and conquer sort of this reconsolidation, ultimately thinking about how some of these interventions, we got to put them back together to deal with the big picture, especially in the clinic. Talk a little bit about how your sort of thinking throughout this evolution has changed, because it's only recently that you've moved into this rather unique and timely space to think of the combinations and the unique interactions between what you've been developing, ultimately how they're going to translate clinically.
Sure, yeah. I mean, actually, there hasn't really been any evolution of my thinking in all of this. It's more a case of the time having come to be able to do the things that we're doing at LEV Foundation. So, 20 odd years ago, when I came up with this classification of the types of damage that accumulate in the mammalian body during life, and the corresponding ways that we might go about repairing them and eliminating them so as to reverse biological age. When I came up with all of that, some of the things that were on my list were already established, especially, stem cell research was definitely a thing, and
Right.
stem cell therapy was on its way. And of course, this was this is what I said was the right way to go about dealing with cell loss, with cells dying and not being automatically replaced by cell division. And so that's all very well, but of course there was still a great deal to do in that area. Stem cell research is still very much a research area which still needs progress to be made. Um, Now, in other areas, things have moved in directions that are pleasantly surprising. So, one particularly good example is the elimination of senescent cells, which was again one of my seven deadly things. Back then, 20 odd years ago, my expectation was that we would have to do something rather elaborate involving suicide gene therapy or something like that to get rid of these things. And that is still an option, and it's being pursued by certain groups. But it seems like, to a fair approximation, we can selectively remove senescent cells with small molecules, which is, mind-blowing, really. It's astonishing that this is, I mean, I would never have considered that possibility 20 years ago. Um, and of course, there's been progress in other areas as well. Gene therapy is getting better,
Hmm.
obviously, especially in mice, but not just in mice. And is indeed being used now, especially for problems in the eye. The eye has the advantage when it comes to gene therapy that it has almost no immune system, and therefore one can do things with viruses that one can't really get away with in the rest of the body, and so it's a kind of testing ground for a lot of things. And indeed, one of the ideas that I put forward 20 odd years ago was with relation to macular degeneration, the use of gene therapy delivering a bacterial enzyme, or the gene for a bacterial enzyme, of course, um, to break down the molecular waste products that accumulate in the back of the retina and that drive macular degeneration. And that was a very ambitious and radical idea at the time, and it took a long time to get it to go, get it to work. But eventually, it's moved through the various stages, and now it's in the process of being sold to big pharma. So it's quite a success story for the whole damage repair approach.
Hmm.
But you're absolutely right that at LEV Foundation, what we're doing is we're leveraging these various bits of progress. And rather than continuing the work that has been and is being done at SENS Research Foundation, which is focused on the early stage development of the most difficult damage repair areas, instead we're taking the ones at the other end of the spectrum that
Right.
have made the furthest amount of progress, especially in mice, and we're combining them. We're saying,
Right.
okay, what happens if you stick these things together in the same mice at the same time? So back in November or December, I bought 1,000 mice from Jackson Labs, and for the past few months now, we've been treating them with four different interventions: a stem cell therapy, a gene therapy, a senolytic, and also a CR mimetic. And we are very interested to see what happens. At the moment, of course, the mice have only been in the program for a few months, but we did start the work in middle age when the mice
Right.
were already 19 months old, which is about 1 year to go before their life expectancy for the strain that we're using, which is C57 Black 6. Um, so I would be hopeful that by as soon as the end of this year, we will see sufficient separation of the survival curves to be able to draw at least tentative conclusions. Of course, we're not just measuring survival; we're also doing all the things that any experiment of this nature always does, looking at function, looking at health of the mice in various ways. First of all, the physiological ones, whether it's visual like kyphosis, or whether it's function like memory or grip strength, things like that. And we're also taking blood samples, measuring various things as you would expect,
Hmm.
and also we're culling a few of the mice every so often so as to see things that you can't see without doing that.
Hmm.
Yeah, so it's a terrifyingly ambitious and audacious experiment. Um, in general, there has emerged a pretty clear understanding within the expert community that now is the time to start doing
Yeah.
combination therapies and indeed start doing combination late onset therapies.
Hmm.
But what nobody except us is doing so far is things that are that require to be injected. Basically
Right.
everyone else is sticking to things that are only orally available, and we very much take the view that that's not going to be the real McCoy. It's only going to achieve a limited amount.
Mhm, mhm. And I'm glad you pointed out the sort of the number of mice you're dealing with here, because I think when people normally hear animal studies, they think a couple mice, but this is no joke, especially when you get into these numbers, not just doing all the experiments and analyzing them, of course, sacrificing them at some point and analyzing everything physiologically, all the biomarkers and all that. But at the end of the day, sort of getting all this data analysis done right. As you're talking, you're starting at 18, well, 19 months. You're looking at these increases in mean and maximum lifespan. Talk a little bit, if you would, because I know you have in this first, and I'll call it sort of this first cassette of therapies. You have the senolytic in there, you have the stem cell therapy, as you mentioned, but then you also have a couple things like the telomerase reverse transcriptase and the rapamycin, which I don't normally associate those with Aubrey de Grey thesis of aging, just because they're great, but I think of them as the sort of the messing with metabolism stuff that we normally put over there when we talk about Aubrey de Grey. But say a few words about just. I know the senolytic and stem cells, as you were mentioning, they've had their evolution, and hence we're testing. But how did you choose rapamycin and the mTERT work as well to combine here?
Yeah, really, a large part of our prioritization for this first experiment, as you say, we're going to be doing a succession of these things over the years. A large part of how we made our decision was based on prior results.
Yeah.
We wanted to look at what other people had achieved in terms of individual interventions that had succeeded in increasing mean and maximum lifespan in normal mice, like the ones we're using, starting in middle age, starting at 18 months or thereabouts. And of course, rapamycin has very much achieved that in multiple studies over the past decade. And so has mTERT gene therapy in a couple
Right.
of studies.
Sure.
The first one being from the very well-respected group of Maria Blasco in Spain.
Yep.
The success of telomerase gene therapy in extending maximum lifespan was a bit of a shock to
Mhm.
everybody, I think, early on. Maria has pretty much explained it now. Essentially, it comes down to the fact that mice are spectacularly bad at maintaining telomere length and repairing telomeric DNA damage. So they lose telomere length at a very much more rapid rate than per cell division than longer-lived mammals do. And essentially, this means you have a great deal of non-uniformity of telomere length, and since the shortest telomeres are the ones that make cells unhappy, you end up with, a benefit from augmenting the amount of telomerase activity in the body, even despite the fact that mice express mTERT, pretty promiscuously naturally. That's why it was a surprise, because you think, if something's there naturally, you don't need more of it. Anyway, so yeah, we thought we really ought to include this. But actually, part of the reason was also that we wanted to do something in the gene therapy space, the
Right.
systemic gene therapy space, because we know that we're definitely going to want to do gene therapy things of other sorts later on in subsequent work. Yeah, so that's really why we chose those. The, the fact that a CR mimetic, such as rapamycin, is,
Mhm.
as you say, it's more messing with metabolism rather than damage repair, is something that we very much recognize. And honestly, again, we're thinking ahead a bit there. We're
Okay.
thinking that maybe the important thing to do here is to address not only the the basal problems with aging that constitute damage accumulation, but also the things that essentially accelerate aging that exist in typical mouse husbandry. Mice, when they're eating ad lib, they get fat,
Mhm.
and that's bad for them. And we're thinking maybe next time, maybe we haven't made this decision yet, but maybe next time we will just give all the mice rapamycin as a baseline, right?
Got it.
Um, uh, or perhaps do bona fide CR with calorie restriction. We don't really haven't made that decision yet, and it may not be the only thing that we do of that nature. So, for example, one other thing that mice are definitely that's definitely bad for mice is inactivity. And most mouse experiments are done in cages that don't even have running wheels. And certainly our experiment right now is being done that way, largely for reasons of cost, to be honest. But we're already looking hard at the possibility of doing the next experiment with smart cages, which have certain cost savings in terms of manpower for getting data, and indeed you can get higher quality data than you can if you're relying on people. Uh, but also, these things have running wheels, and you can measure how much each individual mouse is using a running wheel, even in a cage that has 5 mice in it, which is a confounder if you don't have the the detection. So there's a lot of thinking going on about what the next experiment and the one after that will be about. Of course, one thing that I have to emphasize all the time is that right now we don't have the money to do the next experiment, and so I am vigorously out there trying to change that. But these experiments are expensive. That's another reason why people don't do them. This experiment is costing north of $3 million. And that's despite the fact that we were very successful in minimizing costs relative to what an experiment like this would normally cost. The people we're working with that I call life sciences, who are actually conducting the experiment, have they're very close friends of ours. They that they're very much mission oriented, and they've been very creative in finding ways to keep the costs down.
That's an excellent quality of a partner. That's all I'll say about that. But let's say money wasn't the issue for you're going to have in a little while some very impressive data from this first, I'll call it a cassette of these interventions. With the money in the bank, what comes next down the line here? Is it to put another cassette together based on, say, the complex the interventions that say still sit in sort of SENS, and whether it's cross-link breaking or mitochondrial shuffling, all that other stuff? Is there a concept when you think to build another cassette of these and then do that test? Is it to gradually add intervention 5 to these 4? What would you want to do, assuming that, okay, maybe we'll get to robust mouse rejuvenation after this, we don't know, but say this is RMR 1.0. What do you want to see for the next couple RMRs that come along, based on the exciting results that we all expect you're going to have shortly?
Yeah, we so I mean, I think you're asking the right question there, because this is both a push towards bona fide RMR, towards bona fide robust mouse rejuvenation, which I'm these days defining as extending both the mean and the maximum lifespan of middle-aged mice by at least a year. So taking, these are mice that started at 19 months, average lifespan is about 2.5 years, maximum lifespan is about 3.25 years. Adding a year to both of those numbers, so it's 3.5 years and 4.25 years. If we can do that starting in middle age, starting at 18, 19 months, then that's probably that's probably about 3 times more of an increase than anyone's done before. And I believe that kind of step change in the amount that we can postpone the health and death, obviously, of normal mice is the kind of thing we need to change the conversation completely. To actually have all my expert colleagues be out there saying, this is we can no longer say that aging is immutable. Right. And of course, translatability to humans is a huge part of this. We definitely know that things that work in mice don't usually work in humans, but they work more often in humans than things that don't work in mice do. So it's still worth doing the experiment. And honestly, my feeling is that damage repair interventions are more likely to translate to another species, such as humans, than pharmacological interventions. So we'll obviously see whether that's true in due course. But yes, I mean, I think basically as time goes on, and especially to the extent that we can bring in sufficient funding, we will want to do a relatively rapid succession of these kinds of experiments, maybe as many as 2 a year. And we will definitely want to combine different interventions, and as you say, ending up probably combining more interventions as time goes on. The idea basically is we'll just keep going as far as we can, as long as we continue to see progress in further postponement of health and of health problems and um, survival.
Mm-hmm.
Then we'll keep going. There's nothing special about 1 year.
Excellent. Um, it's interesting in your one of the lines I remember from your book, Ending Aging, is that, when you finally succeed at RMR, the first thing you're going to do is head off to Madagascar, and I maybe you still think that, but I doubt you're going to do that. But ultimately, when you do succeed with RMR via iteration 1, 2, or 3, next comes obviously a bunch of steps to get you into the human clinicals. And there was this article. I mean, there's a paper that just came out. It was literally, I think, less than a week ago, by this group known as the Longevity Biotechnology Association. They published this piece in Nature Biotech entitled "Defining a Longevity Biotechnology Company," with a defined strategy of developing an intervention against the traditional disease of aging, and then at some point in the future, developing that same intervention in some health span / multimorbidity study, a la TAME. Yeah, it's one approach, obviously, but as you were just pointing out, with these combinations, we are at a unique regulatory time where groups like FDA and EMA and so forth have produced guidance to say, hey, if you want to show up with rapamycin plus TERT plus a senolytic plus a stem cell therapy, you can do it, as long as you design everything appropriately. I don't know if you could say a few words about sort of your vision for where we sit in 2023, and what you think, per that RMR clinical intervention, you would like to do, whether it's in 2026 or whenever the time comes, because you do have the option to put one of these cassettes now in a patient early on in the process and not wait 15 years before you test drug 1, 2, and 3.
Yeah, right. So the regulatory environment is changing, certainly. The TAME trial, of course, even though it hasn't happened yet, the fact that the FDA rubber stamped the TAME trial, the
Right.
design of it, and specifically the clinical endpoint, is an enormous piece of progress. And similarly, the changes to the ICD codes that the World Health Organization put in place quite recently, these are very big things. Now, if we think back and we ask, why are they big? What is the potential impact? The answer is really its impact on incentive structure.
Yeah.
Its impact, especially in the private sector, on the pros and cons that decision makers, people who write big checks, will observe, as regards putting money into the very expensive development of therapies that might have a broad-based impact on health in humans. The the problem that has existed is definitely that if you can't get if you don't have a clear path to regulatory approval of something, then you're never going to make back the money
Right.
that you spent in developing it. So you're not going to spend
Right.
that money in the first place. And honestly, at this point, I'm not sure how thoroughly or how rapidly the decision makers in big pharma are appreciating um, the impact of these two things I just mentioned. I think it may be that they're still a little bit stuck in the idea, well, aging's not a disease, we can't really do anything with it. Now, of course, at the moment, we're looking at a different incentive structure problem, which is that the things that we are testing, whether it's the things that LEV Foundation is testing in mice or whether it's the TAME trial, these things are not something anyone can make money out of. metformin's been off patent since before you and I were born. Some things are just not patentable at all. It's like it's hard to see how to make money out of that. So in that sense, from the private sector's point of view, the things that we're doing are really emblematic rather than being direct steps towards things. But I think that's okay. I mean, rapamycin is a fine example. The minute that rapamycin hit the headlines with the finding that you could give it to middle-aged mice and it would be quite effective, people got on the case of figuring out analogues of it that worked better and had fewer side effects and so on. So now we have this entire industry of rapalogs, which are moving towards clinical trials, of course. So I don't really see that as an issue, but it is something that decision makers in the private sector need to actually think through in order to see where they're going.
Aubrey, you've throughout the last couple decades, you've put together pools of investment for your work from traditional investors, from some of the non-traditional stuff in terms of the crypto and the airdrop and all that stuff. Give me your report card for sort of the longevity investment scene as we sit here in 2023, because it seems like the numbers are getting bigger. But when we're talking about the early stage funds or even some of this moonshot money, Calico, Altos, Evolution, some of the stuff that we see, it still seems a lot of the money's flowing into sort of the early part of the funnel, a lot of the early stage. Sort of evaluate what's happening now, and as you're out there, not just doing your stuff, but obviously continuing to fund these types of mega projects.
Yeah, I mean, if we look at the field overall, then certainly the headline is that the amount of money that has come into the field over the past couple of years especially has totally ballooned. It's absolutely spectacular. But the difficulty is that money is very unevenly distributed.
Yeah.
You've got lots of money going into certain areas that have caught people's imagination and or actually made good progress in the past couple of years. The big beneficiary of all that has been partial reprogramming, which is the main focus of Altos, and it's a major focus of Retro and one or two other places. But of course, there are other examples where big money's gone in. I certainly would include cancer immunotherapy here, because even though it's not a new area, it's definitely an area which was catapulted into a much bigger position by the discoveries of checkpoint inhibitors and CAR-T only about a decade or more ago. There's lots still that needs to be done to make these things really work ubiquitously against all forms of cancer, but progress is definitely being made. And indeed, companies that are doing kind of adjacent work that might potentiate things like CAR-T and checkpoint inhibitors are also doing pretty well. So one company I could highlight is Nanotics, which is looking at ways to essentially make cancer cells more visible to the immune system by getting rid of the chaff that cancers shed in order to hide themselves. That's a company that's done very well recently and is now in clinical trial work with multiple major clinics, Mayo Clinic, Cleveland Clinic, places like that. So this is definitely cancer immunotherapy is a kind of poster child for where we ought to be going.
Right.
But yeah, I mean, the areas that are still pre-investable, the areas that are still at a relatively early stage just because they're harder, are definitely not seeing that kind of huge uptick in additional funding. And that's kind of because, most of the people who are writing these checks are investors rather than donors. They want to make money back, and anyone who wants to make money back wants to make it back soon. And therefore, they're not really incentivized to put money into the more challenging parts. So, I've definitely nailed my color to that end of the spectrum in terms of making sure that things that are most difficult, but just as vital as the easier things, don't get left behind. And so I'm out there making sure that they don't. And I should probably mention that LEV Foundation, even though right now its flagship project is this combination stuff, we definitely have an ambition to start projects in that are a bit more like the projects at SENS Research Foundation, that are individually targeted at this or that type of damage.
Mm-hmm. Mm-hmm. Let's talk a little bit about one of those, because robust mouse rejuvenation is clearly, as you're saying, the core of what's happening. But you do have work in cryopreservation of organs, and again, this is an area near and dear to me. And as I've been doing this show the last couple of years, I've had the bioprinters and the ReCell D-Cell and the organoid folks and everyone coming through doing really amazing work on this front. But this stuff is still it's still quite early. Say a few words about what you're doing with the is it pronounced Kinese Bio or Kinese?
It's pronounced kinase.
Kinase, okay.
And we gave a bunch of seed money to Tanya Jones to reboot really the work that she was doing over the past several years at Aragos. And the reason I made that decision was really because at the moment cryopreservation of solid organs is something that doesn't work. You can't do it yet. And if we could do it, it would be enormously valuable, not just financially, but in terms of people's health, because huge numbers of people currently die on waiting lists, right. Waiting for a replacement organ, and that's simply because you've got to find an organ that is sufficiently immune compatible. So that you can, obviously you still need immunosuppressants, but if it's reasonably immunocompatible, then it's doable. And the organ has to be donated in a manner that allows it to be extracted from the donor and put into you within a matter of hours, because that's the time that it takes for organs to just disintegrate and become non-functional. So the ideal situation would be able to cryopreserve such organs and have whole banks of them. So it didn't matter how long ago the donor died, you could just fish it out of the bank and take it to the recipient and just warm it up right on the spot and stick it in. And so Kinase has technology that, in my view, is by far the most promising in this area, involving a method for very greatly accelerating the rate at which you can cool an organ after you take it out of the donor, and of course the rate at which you can warm it up afterwards. This matters a lot for the avoidance of ice crystal formation, which is the key reason why organs are become unusable if you freeze them. And there's another aspect that is the big challenge for cryopreserving of organs, which is fracturing, actual just large-scale cracking, which again is also avoided by this particular method that involves pumping cold helium through the vasculature. But that's really a bit of a left field thing for LEV Foundation. It was a one-off seed funding. We're not looking at funding that project ongoingly. It's really just putting Tanya and her people in a position to hit milestones that will allow them to get funding from elsewhere.
No, but nonetheless, it's an important piece of the rejuvenation equation, as you point out on the site as you talk about it, and it gets me thinking. I've had the ability to profile sort of many of these new groups, some government, some foundation based, that are sort of mimicking the model that we have here in the Defense Department called DARPA, where they're sort of creating these sandboxes, let's say, for people to play in, whether it's organ regeneration. I mean, I just had Welcome Leap folks on, and they got something going on in kidney, sort of by artificial kidneys, and ARPA-H, which was just formed, focusing on cartilage, but nonetheless, sort of very interesting environment that worked well for the Defense Department that others are trying to set up. And I'm just, as you're out there and connecting through sort of Rejuvenation 2023, any interesting other interesting models that you see on your journeys per some of this, as we're saying, that the ability to experiment with some of this stuff that might take a little longer, but nonetheless, giving smart people a lot of money to iron out, let's say, the early stage stuff that normally most of us would get stuck in the valley of death, let's say.
Yeah, I mean that's really what the non-profit sector is for, of course.
Right.
And when you're right to mention ARPA-H. There's great hopes that we have there, but at the end of the day, ARPA-H is going to, rather like DARPA, it's going to be very milestone based. They're going to be taking a fail early but often kind of attitude, and I think it remains to be seen how well that will work in practice. The projects that they are already thinking about doing are very valuable, no question. But I don't know quite how the decision making is going to play out. We're going to have to look at it for a few years and just see, I think. But yeah, I mean, there's in the nonprofit sector, one of the really good things is that over the past few years, there's been an enormous influx of funding from people who are pretty wealthy and young. And the reason I mention that is simply because there seems to be a bit of a spectrum there, that the younger generation seem to have, like, they haven't lost the ability to aim high or the inclination to aim high, yeah. and they are willing to, to embrace the logic that says that, that this is a good use of their money to just let the best people in the world have a good go at something that's extremely difficult. So we're seeing that. So there are some things being worked on now by very good people, good friends of mine, people we've worked with, that honestly, I would say are more ambitious than the kinds of things that I've been talking about in relation to SENS. Probably the most conspicuous example is a professor at Albert Einstein College of Medicine, Jean Hébert, who has been working with us for several years on a really clever way to replace neurons that essentially involves creating them as microglia, as cells that behave like microglia, and then basically genetically transforming them with a drug so that they start behaving like neuronal stem cells after they have migrated around the brain. It's a very clever idea. It's now been formed into a company called Glionics, and I very much encourage people to look that up. But Jean himself is now really prioritizing something much more ambitious that involves essentially removing large chunks of the brain, like 10% at a time, and replacing it surgically with essentially new neural structures grown in the laboratory. This is essentially based on the idea that one can gradually inactivate certain areas of the brain and cause the information that was in that area to essentially migrate out into neighboring regions, such that the removal of the inactivated region will have no cognitive consequence, in theory. And then you stick this new stuff in, and it forms linkages, forms synaptic connections and so on with the surrounding areas that you haven't replaced. And the idea is that you would do this serially, however often you'd need to, so that eventually you'd be replacing the whole brain. It's interesting, really. I mean, on the one hand, I think this is terrifying, but Jean is a very good neurobiologist, and so I'm reluctant to dismiss it out of hand. And he has already obtained some funding for this work. And other people have obtained funding for a similarly ambitious work that I would say is perhaps too ambitious, perhaps. And so, because it's a perhaps, because I might be wrong, I'm very happy that this has happened, right? And it has typically come from the younger crypto crowd,
Right.
this money. Now, it's interesting actually to explore a little bit more about why Jean wants to do this. I mean, because he accepts that this is a very, very, high risk, audacious approach. So you might ask, why is it needed? And actually, this is something where Jean and I disagree. I think he is unduly pessimistic about our near-term ability, can't do it yet, but soon, to repair the brain at the molecular and cellular level sufficiently comprehensively that we won't need to do it at the surgical
Mhm.
level. Um, he points to things like long-lived proteins, especially the extracellular matrix, that obviously do accumulate post-translational modifications and changes that may impact the function of neurons and glia for that matter, over time. And even though this is a very poorly explored area, I'm certainly comfortable with the concept that there is such a problem to fix.
Mhm.
The question is, how difficult would it be to fix? And obviously we've got those same problems elsewhere in the body, um, in the periphery.
Right.
Uh, if we just look at the extracellular matrix, I've focused historically very strongly on cross-linking,
Mhm.
which is something that changes the elasticity of the extracellular matrix. Nobody's really been able to show whether that matters in the brain. The brain doesn't do what, like, arteries do. It doesn't have to flex all the time, or at least not at the macroscopic level. But that doesn't mean that there is no consequence. So, I'm willing to entertain the idea that we need to do something in the brain to reduce cross-linking. But the fact is, we are already doing something. It's got as far as being spun out of the company, Revel Pharmaceuticals,
Right.
that came from work that we funded at SENS Research Foundation. So this is definitely happening, and I see no reason why any discoveries that are made that work in the skin or the arteries won't also work in other parts of the body.
Hmm.
Um, and there are other issues like turnover. So, for example, one thing that we are now quite excited about is the idea of stimulating turnover of extracellular matrix that has been damaged, whether
Okay.
by cross-linking or in other ways. There's another company that I'm quite excited about called Elastrin,
Hmm.
which is doing this. It's got a clever trick for especially addressing the calcification that happens in the vicinity of damaged elastin. And that company, well, again, you could ask, is this really ready for the private sector? But apparently it is. Our great friends at Kazoo in Germany, whose non-profit arm Forever Healthy has worked with SENS Research Foundation a lot over the years.
Yeah.
They decided to invest in Elastrin. They worked very closely with them to make sure that the team at Elastrin had all the qualities it needed. And so now that's being taken forward. And so, all of these things are still happening, and they are very much happening, and they very much lead me to believe that pessimism about the ability to do all of this at the molecular and cellular level is probably premature. Same
That's
goes for
fat.
same goes for other types of pessimism. So I've got plenty angry over the years at credentialed people coming out and saying, "Oh, we can forget about all of this business of living forever because there's this natural limit to human lifespan." And people will, typically do this on the basis of demography. They will say, like, "Oh, you know, maximum lifespan doesn't seem to be going up anymore, and there's this kind of natural limit." And of course, like, the error in that logic is extremely obvious. Namely, anything that you look at demographically relates to people who are already alive and
Right.
already dead, indeed. So, in other words, definitely by definition, people who have not had the opportunity to benefit from therapies that have not yet been developed. right? And therefore it says absolutely nothing about what we can do in the future.
Right.
And yet, because it gets said in a terribly, solemn manner by terribly credentialed people, nobody bothers with that little detail. And it entrenches the opposition or at least apathy regarding the work that we're trying to do here, which is, really, really not a good thing. It really
Yeah.
slows things down. And the thing is, it's done in a well-meaning way. People are trying to, focus us on what can be done and what can't be done. It's just that they have to get it right. And sometimes I feel like there's too much confusion between analysis of existing data and there's too much readiness to jump to conclusions about what's possible. So you interviewed Peter Fedichev fairly recently, and I
Hmm.
must say I don't often watch interviews that are more than an hour long or lectures like that, but I watched this one because it was so good. You were not just asking the right questions; it was just that Peter has very much got what it takes to describe a really complicated concept in non-technical terms. So
Right.
I was very impressed with how he described things. But I'd like to kind of explain where my thinking is on this
Sure.
because it's recent. It's something
Absolutely.
that's very much in the public imagination right now. So what Peter
Please.
did was he did some very sophisticated longitudinal analysis of data on health records and on epigenetic age in large numbers of people. And he was able to extract, well, to keep it as simple as possible, the conclusion that there are really two strands to aging viewed at the top level. There's a strand that proceeds pretty much linearly with actual calendar age. And then there's another component that proceeds pretty much exponentially. Now, essentially, what Peter was able to show is that the exponential one doesn't kick off until rather late in life. So that through most of life, you've got, not of adulthood, you've got this linear thing, and that's really all you've got. And um, I mean, I don't think he really tried to say that this is a new finding, and it isn't really new. It's a kind of a restatement of the way that I describe aging as having these two processes, a
Hmm.
process where metabolism generates damage and a process where damage generates pathology. So essentially what he's pointing out, which is absolutely right, is that there's a positive feedback loop from pathology back to metabolism. Essentially, the worse the pathologies get, the
Yeah.
more they get in the way of metabolism, and the more they limit metabolism's ability to slow down the rate of subsequent accumulation of damage. And to be honest, there probably is a bit of a positive feedback loop from damage directly back to metabolism, but it's
Hmm.
very, very much weaker, so you can basically ignore it. So it's only when the late life process of damage creating pathology, when that kicks off, that you start to get this exponential thing kicking in. Now, one thing that Peter suggested and concluded that's quite interesting, and I haven't really decided whether I agree with him on this one, is that in mice, you don't really have this period of young adulthood where essentially not a lot is happening and you've got this just this linear accumulation of essentially a harmless damage that only becomes harmful when there's too much of it later on.
Yeah.
Um, he said, well, basically, you've got the pathology starting pretty much at once, or at least by adulthood, and so you've got the exponential process happening throughout the period that you're interested in, throughout the adult mouse.
Yep.
Now, going back to I mean, he didn't actually present data on that in this recent work that came out on bioRxiv last year. Um, but what that paper did do is it referenced some earlier work from his group
Okay.
that I've had a look at. I must say I was not sufficiently familiar with it before. However, I'm a little nervous that he's not really comparing like with like there, because the longitudinal data that he was looking at in the earlier work in mice was phenotypic and did not include the epigenetic age type stuff. So I need to have more of a conversation with him about that.
Hmm.
Um, but that's not what I want. Why I wanted to bring Peter up. the main thing I wanted to bring Peter up about is the conclusion that he came to, that there are limits, in fact it's in the title of the paper,
Right.
to how much we can do about aging. He basically, pulls out of, I would say, honestly, thin air, the conclusion from this longitudinal data in humans that the exponential part of aging, which happens late in life, is at least largely, theoretically, or perhaps even practically, amenable to repair, to rejuvenation. But that the linear part is just very, very, very much harder to, to address with any kind of damage repair. And honestly, I think he's wrong. I think that there are definite options here for addressing those what he calls thermodynamic aging, such as especially epigenetic noise. He briefly mentions partial reprogramming in the paper, and he kind of dismisses it and says, partial reprogramming has had interesting results, but basically it's only going to do part of the job. And he doesn't really even try to explain why it shouldn't do the whole job. And honestly, I think it probably will do the whole job. So Peter and I had a very long and detailed conversation about this at a conference we were at in Montenegro a month or two ago, which was filmed actually. It was
Yeah.
because people were very interested to hear what the two of us had to say to each other, and we came to the conclusion that yes, more experiments are needed, so to speak, in order
Mm-hmm.
to answer this question. But this is the kind of thing where I feel that prominent people in the field have to be really careful with the risk of being overinterpreted, especially if they say anything even tentatively pessimistic, because the wider world is desperately looking for reasons to be pessimistic as a
Right.
way to perpetuate the what I call the pro-aging trance, and continue to put aging out of their minds and get on with their miserably short lives.
Right. Right. No, it's a fascinating review of what Peter had to talk about. I saw the piece from the Montenegro get together. But yeah, man, I love to have both of you on at some point, and you can go further into to this. But while we're on there, you mentioned obviously earlier on sort of the triumvirate of Altos, New Limit, and Retro, and the 3+ billion that's gone into partial reprogramming now. I'd love to, you've talked to the public square on this topic in the past. Reprogramming hasn't been an intrinsic part of your portfolio to date, but I'd love to, get your thoughts on where we are with that, because my assertion is, and I have, opinions on both sides with it. As interesting as partially reprogramming something is, it doesn't take into account everything, and the fact that we're hiding out currently in age reversal because we're afraid of stepping into fate reversal because of all the teratoma stuff that the IPS folks avoid. But nonetheless, there's things where we may need some type of fate reversal along the way, whether we're dealing with what happens in regeneration processes, whether it's just, hey, I have inappropriate scar tissue or fat tissue or precancerous cells or whatever that I don't want reprogrammed. I want to change them into something else potentially. Give me your 2023 highlights on where you think we are. Obviously, Altos and the gang is going to be discovering a lot of stuff the next 5 to 10 years, but thoughts on reprogramming, partial reprogramming, or some other variant?
Yeah, so I mean, really, there's two things I want to say. First of all, the cancer risk. So people are, of course, concerned about teratomas. When Manuel Serrano did the proof of concept experiment of just expressing OKSM constitutively, his purpose was to find out whether it would actually work at all, and the readout showing it did work was precisely teratoma formation.
Yeah.
So the next step, the obvious next step, which was what Belmonte did, was to to express this transiently and figure out the right amount of expression to achieve rejuvenation without teratomas, and that's all very well. But what I'm much more worried about is the risk of regular types of cancer.
Yeah.
Because when you do reprogramming in cell culture, you are not you're factoring out the possibility of genetic heterogeneity in the
Right.
cells in question. When you do it in vivo, you've got a lot of cells that are already, mutated in various ways that may make them nearly cancerous, right? And the thing about and this is not, this is pretty obvious, and so of course, Belmonte knew this, and so did everybody else. But where I feel there is over-optimism, overconfidence, at least in what's being said publicly, is that mice just don't live long enough to give a readout for whether partial reprogramming is actually oncogenic.
Right.
They, the cancers that will be created de novo. There will be individual cells which already have most of the mutations or epimutations necessary to become cancerous. And what you're basically doing with partial reprogramming is you're hitting their epigenome with a sledgehammer, and particularly you're hitting their cytostatic network with a sledgehammer,
Yeah.
so that they may be pushed over the edge into uncontrolled cell division. And you won't know in the time that the mice are alive, because the cancers that kill mice normally are cancers that start really, really early in life.
Yeah.
Cancers that are initiated when the mice are already in middle age will not have time to grow big enough to be problematic. Whereas in humans, that's very much not the case. So I really don't think that risk has been properly evaluated or eliminated. Therefore, I'm actually much more interested in the partial reprogramming space in alternative approaches to partial reprogramming that do not use OKSM at all.
Right.
In other words, genes which have the potential to rejuvenate cells, to turn back their developmental clock somewhat, but even when expressed constitutively, are unable to push them all the way back to pluripotency. So Mike West at Ajax has been pursuing that general idea for quite a while now. And honestly, that work is desperately in need of further funding. If Hal Barron or anybody or Rick Klausner or anyone at Altos is listening to this, I would urge you to get in touch with Mike West and perhaps buy his company from him. Because this is work that could enormously accelerate the path to the clinic for partial reprogramming, which at the moment I believe is really blocked by this risk of cancer that I just spoke about.
Aubrey, you mentioned the Montenegro event from a few weeks ago. You're sitting there on the West Coast right now of the United States. I'm here on the East Coast. Any other interesting pockets of longevity geographically, stuff that's happening maybe in interesting locales? I mean, we hear about these occasionally, but I don't know if there's stuff that you may be aware of that's happening for some of these countries. I had some of the ambassadors on from Costa Rica recently that they're doing some really interesting things down there in terms of taking CAR-T to Central America and creating sort of not just a bioeconomy, but thinking of longevity economy. Any other interesting sort of pockets of geographic longevity arbitrage that you see springing up that may be interesting to mention?
Yeah, so geographically is not really how I would put it, because the Montenegro event was what they called a pop-up city. In
Right.
other words, they basically took over this town, or at least this resort, and for a couple of months, explored futurist areas, crypto, longevity, etc., AI, and it was a great community. It was a great team building exercise, but even though there's definitely a great deal of enthusiasm for doing it again, it may not necessarily happen in Montenegro. Now, it may very well happen in Montenegro because the government there is very keen on all of this. They think that they see a benefit to their economy and so on. And of course, the same applies in other parts of the world. You mentioned Central America. Yeah, absolutely. So there's definitely, energetic conversations going on there to try to modernize legislation and regulatory frameworks so as to, declare aging a medical problem or a disease or whatever, and to facilitate the development of cutting edge therapies that might just take a long time to get through the more traditional regulatory frameworks that exist in the bigger economies. Of course, there's a lot of interest these days in biohacking, especially in the longevity space. People, foremost among whom, I guess, is definitely Liz Parrish, who are out there, doing things to themselves and working with, working in countries that have a more liberal jurisdiction in this area. I very much approve of this. I think that there will always be early adopters, people who are comfortable taking risks that most of us would not want to take, and whose experience, whether positive or negative, can very valuably inform the rest of us. And of course, you can always say, well, you really need randomized, controlled clinical trials, and I'm not denying in any way that that is the gold standard. But I am very much denying the contention that anything else is basically of zero value, which is the kind of message that some people like to put out.
Right. Yeah. Aubrey, while we have you, anything else hot on the calendar for you for the rest of 2023? I know you have a lot of the outreach and conferences that you're going to be showing up at, but anything else that we should know about per LEV Foundation in the coming months?
Yeah, absolutely. So, I mean, of course, the main thing is a conference that I'm not just turning up at, that I'm actually running along with the rest of my colleagues at the foundation. That is Longevity Summit Dublin, August the 17th through 20th, in Dublin, obviously, in Ireland. It's a fantastic place for the kind of conference that I like to run, which obviously has a lot of emphasis on the recreational component and on community building. The local organisers there, people that are working very closely with us, Martin and Beatrice, are fantastic organisers, and they pulled off a particularly good event last year, our inaugural event, when LEV Foundation didn't even have a name. So, this year, if you go to longevitysummitdublin.com, you will see that the caliber of the speaking roster is just like absolutely everybody is there. It's like, it's the highest caliber speaking roster I've ever put together, and that's quite a statement.
Outstanding. Really outstanding. Aubrey, I just really, as usual, wishing you and the team the best with all this and much success as you get these very ambitious projects started and completed. Again, for everybody that is going to be listening to this particular episode of our show across the podcast networks or watching on the YouTube channel, again, you've been listening to Dr. Aubrey de Grey, President, Chief Science Officer, Longevity Escape Velocity Foundation. Aubrey, again, I want to thank you for taking the time out of your schedule to come talk to us, educate us on what you're up to in 2023. Obviously, thank you for what you do. And it's like to say on this show, thanks for helping to create a better tomorrow for so many people via what you're undertaking. Really great having you again.
Well, it's been my pleasure. Same as always. Thank you so much for having me back.